Hi everyone, welcome back to Heterogeneous Parallel Programming class. We are at lecture 8.3. We will be introducing heterogeneous supercomputing and a somewhat related programming model, MPI. And MPI is really designed to program a cluster of a large number of nodes, and these nodes do not have shared memory. However, what we'd like to demonstrate here is that once you understand CUDA, you can easily understand a programming model that is designed to program a very different type of hardware, but you can do so very easily. So this is a slide shows an example of heterogeneous supercomputing, and it's a supercomputer at the University of Illinois, Urbana-Champaign, called Blue Waters. It's the largest scientific computing supercomputer available to the National Science Foundation community, and it has more than 11 petaflops, and actually has been upgraded to 13 petaflops recently, and it contains 1.5 petabytes of DRAM. That makes it one of the largest machines as far as DRAM capacity is concerned in the world. And when we look at the machine, there are two types of nodes in the machine. The first type of node is Cray XE6 node, and there are 22,640 of these nodes in the machine. And each of these nodes contain two AMD Interlagos chips, and they add up to 16 core modules, 64 threads, and it has each node has a peak performance of 313 gigaflops, and each node has 64 gigabytes of memory, and the two sockets or the two chips all together have 102 gigabyte per second memory bandwidth. It's a very impressive kind of memory bandwidth. And the interconnect that connects these nodes is a Wen-mei interconnect from Cray, and it provides 9.6 gigabyte per second per direction for each node. The more interesting part of the machine is the part that contains Cray XK7 nodes. And there used to be 372 of these nodes. It has been recently upgraded to 4,400 of these nodes because of user demand. And each of these nodes contains one AMD Interlagos chip and one NVIDIA Kepler chip. So the AMD Interlagos chip has 8 core modules, 32 threads, and 156.5 gigaflop peak performance, and 32 gigabytes of DRAM, and it has 51 gigabyte per second memory bandwidth. The Kepler chip has 1.3 teraflops of peak performance for double precision, and it has 6 gigabytes of DRAM and 250 gigabyte per second bandwidth. As you can see, the GPU has about 8 times the peak performance of the CPU chip and 5 times the memory bandwidth. So this is a very typical kind of heterogeneous parallel computing model that we have been assuming in this class. The Wen-mei interconnect is the same as XE6 nodes. So when most of the teams that use the XK7 nodes use the CUDA for the node level programming. However, they also use MPI programming to coordinate execution across nodes. And this is the basic model of the MPI programming. We have all these nodes, and within each node, there are multiple of these processes. So as you can see, it's actually pretty similar to the CUDA thread blocks and the CUDA threads. And but MPI provides a flat view. That is, instead of having node concept, MPI just has all threads. So all the threads are given a flat index, just like the global index in the OpenCL programming environment. And the program in MPI is written just like CUDA in SPMD programming model. That is, each process computes part of the output, but they all execute the same piece of code. And but you can specialize some of the MPI processes by using control flow so that some of the processes will follow one control path and some of the processes will follow other control path. And we will see that in our code example. That these processes will communicate with each other. They don't have shared memory, so there's no such thing as global memory in the MPI model. And all the processes need to exchange message in order to be able to communicate with each other and deliver data to each other. And the processes can synchronize through collectives, and we will see the collectives are going to be very similar to the synchronization primitives in CUDA. So there are some housekeeping MPI, API functions, and so on. The first one is MPI init. So this needs to be executed for all the MPI processes when you bring up an MPI program. And there is an important predefined constant called MPI_com_world. And this is really referring to the MPI group that you belong to with all the allocated nodes. And then there's MPI com rank. This is equivalent to the OpenCL global index API function. So for each process, if the process calls this API function, the value returned in that rank parameter is the index or the identification of the process. So this is really equivalent to the OpenCL get global index API function. And then you have the MPI com size, and this really returns the number of processes in the group that in the entire group that contain your process. So this really defines the total number of processes in this group of computation. So this corresponds to the grid dim concept in CUDA. So let's go through a very simple example, vector addition, just so that you can see the similarity and the differences between MPI and CUDA. So we have a main function, and this code is going to be executed by all the MPI functions. So we define the vector size, and we define we have the PID and NP. So each process will have a process ID, and each process will also have a variable that tells how many processes are involved in this whole computation. So every process needs to initialize MPI, and then you will go and call each process will call MPI com rank. So this gives every process a unique ID in that PID variable. So every PID variable in each process will be the PID variable in each process will be different, and then the com size tells you how many nodes processes there are in this computation group. The total number of processes in the group is requested when you launch an MPI program in the user command. However, the system may or may not give you exactly the number of processes that you requested. So this is the way for you to actually verify how many processes you received after the MPI program gets launched. So we can immediately check if the number of processes is less than a certain number. If it's less than a certain number, that means that the system didn't have enough resource to give you the number that you want, and then you can just have the zeros process to print out a message saying that there's not enough processes, and then then you can just have a abort and essentially initiate abort. All the processes will initiate that abort, and you would all return 1, which is an error code from all the processes. So then if the number of processes is sufficient, then you pass all that code segment, and you get into the real execution for all the processes. So here we show that you can use a control flow to specialize one of the processes, which is NP-1 process, to be the server, and then from 0 to NP-2 will be the compute nodes. So you have this is equivalent to this host, and this is equivalent to the device in CUDA. And so whenever you have a compute node, you will essentially receive a section of the vectors, input vectors and output vector for the computation. So this is why you take the vector size and divide by np minus 1. And after both return, then you will execute the MPI, finalize, and clean up all the data structure and release all the resources, and then you return successfully. So let's introduce a few MPI things that further illustrate how MPI programming is very similar to CUDA. So you can have MPI send, which means a MPI process is sending data to another MPI process. So it takes several parameters. The first one is the initial address of the send buffer, or beginning address of the send buffer. And then the count is the number of elements in the send buffer. And this is the number of elements, not number of bytes. So if you have bigger elements, such as double precision, you will have the same number of elements could be bigger in total size. And the third one is data type. So these are the data types like single precision, double precision, integer, and so on. And then you have the destination, which is the rank of the destination, or the process ID of the destination process. And you can have the tag and communicator, and look at the MPI user guide for more description about this. For now, you can simply use a simple usage that you will not need to know too much about these as a beginner. So now we also have the MPI receive data, and it's very similar to MPI send. It's just that the process receives data from another one. In order for the processes to successfully exchange data, you need to have one of the processes to send and the other process to receive, and they have to match each other in order to get the data. This is actually different from the CUDA communication, where you have the CUDA main copy, but it's usually either from host to device or from device to host. It's a kind of a one-way communication for each case. And instead of having both the host and device to execute these send and receive to be able to connect. So that's the difference. On the other hand, if you look at it, it's actually a very similar. The MPI send receive pair is very similar to CUDA main copy. The main purpose is for one party to be able to deliver data to another party in the system. So here we show the server code. So the NP-1 process is going to do the server. So it's going to do the I/O. It's going to parcel out the input to all the compute nodes, and eventually it's going to collect the output from all the compute nodes and do the I/O. So here, the server process code will have a number of processes, because it's going to revalidate the number of processes involved so that it can actually send the data correctly. And then it's going to call the MPI com size to get the number of processes. You're going to ask me why we need to do the call again. The reason is simple. If we wanted to, we could just have the main program to also pass that number of processes as a parameter. But it's just a little cleaner code if you just call that code again and reduce the number of parameters you need for these, for this function call here. So then we are going to have the number of nodes as NP-1 here, and we're going to memory allocate for the input, the whole input and output vectors, A, B, and output. So if we don't have enough memory in the host, we're going to have an error. But if we have enough the memory allocation, memory that we can allocate, then we go into initializing data. In real programs, we will be reading input from disk or from network. But here, since it's a very simple example, we just randomly initialize A and B. So then we will need to send data to the compute nodes. So we initialize pointers to these input vectors. And then we go into a loop where each iteration of the loop in that server process will send a section of the input A and input B into one of the compute processes. So we're going to start from process 0 and to the process np minus 2. And then we're going to, for each one, we're going to send a section of A and section of B. So after we send the sections of A and B, we will increment the pointer by one section in A and B so that we're ready to send the next section to the next process. So this allows us allows the server process to loop through all the processes. Obviously, if you have a very, very large number of processes, you may need to parallelize this process, further parallelize this sending process. And then once we send all the data sections to the compute nodes, we can do an MPI barrier. So essentially, the server process is going to be waiting at a barrier for all the compute processes to finish their work. And then once everyone else also finished their work, then everyone will be released from that barrier. So then the MPI server process can go and collect the data from all the processes. And so this is why the server process now needs to execute an MPI receive. And then once we finish that process, the server process is done. So as you can see, we have a barrier synchronization MPI, which is extremely similar to the CUDA barrier synchronization or the CUDA the CUDA sync threads. And then so the MPI barrier essentially defines a barrier for all the processes in that computation group. So they will block all the callers until all the group members have called it, and then the call returns at any process only after all the group members have entered the call. So so the compute, you would expect that all the compute processes will only make that call when they finish their computation and ready to deliver the data back into the server. So after the server collects all the output, you would can do the I/O, and then you will free up A and B, and then you will output, and eventually it will return. Remember in the main program, and the main program will do an MPI free, so that you would essentially end the use of all the resources and return. So here it shows the compute process code where the NP minus 2, NP minus 1 of those processes will all be executing this piece of code. So when you come into this piece of code, you also call a MPI communication size, and this gives you the number of processes. The reason is that NP minus 1 is the server number. So if you have 100 processes, then process 99 will be the server number, and that's what you use in your MPI receive and send to identify the server process. So here we allocate memory for the section. Remember, the vector size that you're going to be receiving is a section of the total vector. So these memory allocation are done only for sections of A and B and result. So then you can immediately go into the receive to receive data from the server. So you will receive a section of A and a section of B. So then you can go into the computation where you calculate the output for your section. And after you finish the calculation, you should expect to see a barrier synchronization, which is exactly where we're showing here. And each compute process will call that barrier synchronization here. And then you will, when everyone has finished, then they would call a MPI send so that it will connect with the server receive process receive, and then it will deliver all the data back to the server. And after that, you will release memory for your section. So this completes a very, very brief introduction of MPI. And you will actually see that for most people who use Bluewater's XK7 nodes, you will see MPI code at the top. And then whenever each process executes that section of, let's say, vector addition, it would likely use GPU, and you will see the CUDA main copy to GPU, launch kernel, and then CUDA and copy back. And then you would see the compute node sending the MPI message back into the server process. So this completes a kind of a very, very simple introduction to MPI. But the more important part is for you to appreciate that once you understand a programming model like CUDA, you can actually understand a programming model that is designed to program a hardware at very different scale, a very different kind of communication, and very different no global shared memory, but all the concepts are within your reach. So for those of you who would like to learn more, you can definitely go and read the MPI specification, but also we give a practical introduction to MPI programmers who are interested also in using CUDA in sections 19.1 through 19.3 in the textbook. Thank you.